Hey everyone, what's going on? Welcome to Focus here. This is the continuation of the first video of logistic regression. So here we will see like whatever we have learned about the optimization function, and we will continue on that, like what are the disadvantages of the optimization function that we have learned. Okay. So what we have learned is that this one. So you have to find the optimal W which maximizes the sum of signed distances, right? I mean that is perfectly correct. But there is only one problem. I mean this above optimization equation is affected by outliers. Now, in simple term, what is outlier or what is an outlier? That is an extreme point which is odd one out. It's an error point. Okay, so that is something called outlier. Now, here you can see xj. Xj is a point which is an outlier. I mean, how visually you can see that why is an outlier? Because you can see both the positive and negative points are although separable, but all the points are in somewhat in a similar cluster. But in a vector space, when a point lies far from an original cluster, that is called an outlier. I mean, in simple terms, you can say that, but I'll be having a dedicated tutorial on how to deal with outliers, how to know who is your outlier, when to remove outlier, when not to remove outlier, all these things. But in simple terms, you can think like outlier is an extreme point that hampers this particular logistic regression optimization equation, right? Okay. So let's see one scenario. So what I am showing you that there are around 100 positive points and there are around 100 negative points. Okay, and there is one outlier point which is also a negative point and outlier point, and also in the side of, I mean also what should I say, like with respect to this particular hyperplane, this is in the side of uh, the positive points. Okay, so anyway, this is an outlier point, so that is our main concern. Okay, so what we are saying, okay, we have 100 positive points, we have 100 negative points. Okay, and now what we are trying to do is that we are trying to use logistic regression. We are trying to use logistic regression, and logistic regression say first draws a hyperplane, this hyperplane, say pi 1, where the normal is w1. Okay, now what it is trying to do, it is trying to optimize this particular function. So that means it will try to maximize the summation of signed distances for all the points. Okay, so what I have total 100 positive points, and what I am saying that average distance is 1 unit from the plane, from this plane. Okay, from this plane. Okay, I am doing this first scenario where considering the plane is w1. So for both 100 positive points and 100 negative points, the average distance from this plane is 1 unit. Okay, and and the most important thing is that from this plane, from this plane, the outlier distance is 1,000 unit, because outlier is an extreme point. So it's far away from the actual plane, far away from the original cluster. Okay. So now, if we try to equate this, you try to find out the summation of the sign distance. What you will get for all the positive points, I mean this particular hyperplane will correctly classify all the 100 positive points, right? So the sign distance will be summation of the sign distance for this positive points will be 100 units, right? Okay. Again, it will also correctly classify all the negative points. So again, the sign distance for all the negative points will be again positive 100. Now, now the real fun is happening. Now this xj is an outlier point. From this plane, the distance is 1,000 unit, and it is also on the wrong side. Basically, this is a negative point. This should be on this side of w1 plane, right? But this is on the same side, so it will actually misclassify this negative point as a positive point, right? So the sign distance will be minus because it is misclassifying, and the distance value will be 1,000, right? So now if you do the whole summation, So positive 100 plus positive 100 and negative 1000, it will be minus 800. So for plane W1, we can see the summation of sign distance is minus 800. Now logistic regression, what it will do, it will try to find some other plane which will maximize this distance. Now this is not maximized, right? This is negative 800. Okay, so this is not even positive. Okay, so what it will try to do is that it will find, say, another hyperplane, say this one. Okay, so this is W2 is the normal, or W2 you can say is the normal to pi 2 or plane 2. Now here in this case, what is happening, just see carefully. Now this distance for this outlier is affecting so much that this particular W1 plane has been turned into this W2 plane, and the distance between xj and W2 plane is assuming I am assuming that is 1 unit. Okay, and the average distance from the positive points and negative points is 2 unit. Now think carefully. Now this point, as part of W2 plane, it is correctly classified because it is in the opposite direction and it is actually a negative point. So obviously the sign will be positive and the distance is 1, so the distance will be 1. So positive 1 for the point xg. Now all these positive points are in the same direction of W2, so this plane will correctly classify all the positive points, right? And average distance from this plane is 2 units. For 100 points it will be 200 units, so positive 200 for all the blue points or positive points. Okay, now think, now see, now all the negative points, this all the 100 negative points are also in the same direction. Usually it should be in the opposite direction to be correctly classified, but it's in the same direction. So W2 will actually misclassify these all negative points. So that's why there is a different, I mean the opposite sign, that is minus sign, negative sign. And due to average 2 unit distances for 100 negative points, the distance will be 200. Now if you calculate the total sum distance, it will be 200 minus 200, it will be cancelled out, and 1 will be for this correct classification of this outlier point. Now the summation of the sign distance is positive 1. Now see carefully. For W1, we see the summation is minus 800, and for W2, it is positive 1. Now from the perspective of logistic regression optimizer, it will choose W2 because it is actually maximizing this, right? This plane is actually maximizing the sum distance, sign distance, right? Not W1. But think logically. If W1 were the original or the optimized plane, the accuracy will be much higher because it is correctly classifying all the positive points, it is correctly classifying all the negative points, only one misclassification here. So only 1% of error, right? But here in this case, W2, it is correctly classifying this outlier point. Okay, fine. It is correctly classifying all the positive points. At the similar time, it is also incorrectly classifying all the negative points as positive points, right? So here almost 50% error, right? Right, that is 50% accuracy. So for W1, it was almost 99% accuracy, and for W2, it is 50% accuracy. So a single outlier point is actually judging or confusing the optimizer, right? It is actually confusing. That's why the optimizer is saying that my W2 hyperplane is much better than W1 because it is actually maximizing the sign distance, summation of the sign distance, right? So that is why what we are trying to do is that we cannot use this particular optimization function. We have to do some hack on that. Okay, so I mean the concept of the optimization function will be this: we have to maximize this sign distance, but we have to apply some hacks so that that optimizer or the logistic regression model itself will become robust to outlier points. And what is that hack? What is that mathematical hack, to be precise? That is sigmoid function. Basically the hack is squashing, because if you know, the title of this video is Sigmoid Squashing. So what is squashing means? That is squeezing the, I mean you can think like squeezing a higher value into lower value, something like that, or basically like squeezing all the values, all the real values into some range, into specified range. So there are some quite a few mathematical functions or squashing functions are available. So in logistic regression, we specifically use sigmoid function. Why, I will tell you, but we use sigmoid function. So sigmoid function is denoted by the sigma of x, sigmoid of x, which is nothing but 1 by 1 plus e to the power minus x. Now, if you plot this, if you just plot it in Python or any online tool, you can see like there is a S-like curve. Okay, there is a S-like curve. Okay, so what is happening? Just see, when in the x-axis, when you're approaching to positive infinity, the values are actually squashed and flattened, saturated to 1. It is not becoming more than 1. Now y-axis is actually sigmoid of x, right? And x-axis is a real value, the x value, right? So when you are approaching into positive infinity, when x is approaching towards positive infinity, the value is saturating, the sigmoid value is saturating, and the maximum value is becoming 1. Similarly, when the x is approaching to negative infinity, then the value is squashed or actually saturated to 0, to 0. So that is how the squashing is being done by sigmoid function. Okay, so in a limiting form, you can say that limit x tends to either positive or negative infinity, then sigmoid of x will be positive 1 for positive infinity and 0 for x approaching to negative infinity. Okay, so this is from the mathematical term or from the limiting term. And if you see sigmoid of 0, when x is 0, the sigmoid is 0.5, that is exactly half. So what we can do, I mean, in previous slide we have seen like outliers are extreme points from a particular optimized hyperplane. The outlier distance might be huge, say hundreds of thousands units, right? So that is actually hampering our optimization process and giving us wrong hyperplane. Instead of the best hyperplane, it is giving us the worst hyperplanes, right? So what we are doing, we are nothing, we are just trying to squeezing the sign distance, because the distance is actually hampering, the outlier distance is hampering. So what we are doing, whatever is the distance, pass it through sigmoid and it will be squashed, and it will be in the range 0 to 1, because the minimum value of sigmoid is 0 and the maximum is 1. So every distance, be it 1, be it 0.1, or be it 1000 or 1 million, it will be squashed into the range 0 and 1, right? So what we have done, we have done a simple modification. We wrapped our signed distance term into sigmoid. What we have done, we have wrapped our total signed distance term, that is yi w transpose xi, into sigmoid, and then we're doing the argmax. Now if you think logically, that will actually work and it will be robust to outliers. I am not saying it will be perfect for outliers, but it will be kind of robust. It won't be like the previous one, that's for sure. So now the thing is that, why we are using sigmoid? Because I told you previously that there are quite a few uh, squashing function, like tan h is also there, hyperbolic tan. But then why we are using sigmoid? Now if you see, the range of sigmoid is 0 and 1. The minimum value is 0 and maximum value is 1. So that is one of the major point that why we are using sigmoid. It gives us probabilistic interpretation. If you know from plus 12 mathematics, in probability, how we will define probability? What is the numeric value of probability? It's in the range between 0 and 1. If it is an uncertain situation, then the probability will be 0, and if it is a certain situation, then the probability will be 1. If there is a mixture, then the probability will be in between 0 and 1. Sigmoid also gives us the probability interpretation. So that's why we use sigmoid. It gives us the confidence. It is telling that, okay, sigmoid is actually telling you that this point is positive point, and I'm classifying, sigmoid is telling you that I am classifying this particular query point as a positive point with 95% probability. How it is doing that? Let me tell you a scenario. Okay, so let me first tell you, sigmoid 0 is 0.5. When x is 0, sigmoid is 0.5. Now when we are wrapping our sign distance into sigmoid function, what is our x becomes? Our x is the sign distance itself, right? This distance is actually our x, right? So now This is our hyperplane. This is our optimized hyperplane W. And say we have a point, this point, which is exactly on the hyperplane. It's exactly on the hyperplane. That means the sign distance, this W transpose xi for this point is 0, because it is exactly lying on top of the hyperplane. So W transpose xi, that sign distance as a whole is 0, right? For this point, the sign distance whole is 0. So when you are saying sigmoid of 0, when it is passing, now when it is passing sigmoid of 0, what sigmoid is saying? 0.5. That means sigmoid is saying that this point could be 50% positive or 50% negative. And that's true. If I tell you from this visualization, tell me, if this is a query point and it is actually on top of the hyperplane, is it a positive or a negative? You will surely say that I am not sure, because it's on top, it's not on the other side, it's not on the either side. So it could be positive point, and also it could be negative point. 50% chance it could be positive, 50% chance it could be negative. And that's what sigmoid is telling us, right? When it is 0, sigmoid is telling I'm not sure, it could be 50% positive or it could be 50% negative, right? Okay. Now say this is a point which is far away, say 1000 unit. It might be outlier, it might not be, but I'm saying that it's far away from the actual, not, I mean, from the hyperplane. Okay. Now what is W transpose xi? That is, I mean, what is the sign distance? That is 1000, right? The distance is actually 1000. Sigmoid of 1000, it's I'm not sure, maybe it's 0.99999 and up to 100 nines, maybe. Okay. So sigmoid is saying that if this is a query point, I am 99.99% sure that it is a positive point, or I'm classifying it a positive with a confidence of 99.99%. Similarly, for a negative point, if the distance is 10 units, maybe sigmoid of 10 is 0.95, then sigmoid or the logistic classifier saying that this is a negative point with a probability of 95% confidence. So this is how we can get a probabilistic interpretation, isn't it? So that's why we are using sigmoid function. So ultimately, so ultimately, our optimization function is this. We have to maximize the signed distance, but we are wrapping our signed distance to sigmoid because we want to make our optimizer function uh, outlier robust. So that is the meaning we are squashing it using sigmoid function. Okay, very good. Now there is one small simple thing that I want to share with you. So that is totally from the point of optimization, mathematical or numerical optimization. I will be having a separate tutorial on that, and I will show you what are those things, what are convex function, what are non-convex functions. So basically, now this is not actually convex optimization. What I'm trying to say is that just in simple terms, you can think of that this is our modified optimization function after sigmoid squashing. Now, sigmoid function, you have seen it's not an convex function. Okay. Now, convex function means there are some mathematical implications, mathematical definition. Now, basically, like if you see like x squared, y equals to x squared. Okay, so this is a convex function because from I mean geometrically, I mean visually, you can think like if you want to touch one point from this curve to any other point this curve, and if you draw a straight line and that line is not going outside of the curve, that is called a non-convex, that is called a convex function or a convex curve. Now if there the curve is like that, okay, now this is non-convex because there are some points by you can connect with a straight line, okay, and it won't be outside of the function. But there are some points, say this point and this point, you want to connect to straight line, so it is actually going out of the original function. So this is how you can understand that, okay, this is a non-convex function. But there are mathematical definitions I will cover up when I will do in depth of mathematical optimization or numerical optimization. But I am just saying that if we can get a convex function by any means, that it would be better for us to do the optimization. It's easier ways, but in neural network we will see no loss functions or no optimization functions are convex, or almost all are non-convex, and we have to do optimization on that. But here what we are just doing, we are just wrapping the sigmoid term again with another function, that is log. And what it is giving us, it is actually changing our optimization function from non-convex to strictly convex function. Okay, if you just plot log of sigmoid of x, you will see a convex function is there. So because we are converting it, just because, like, this is, you can say, a mathematical hack, because we are actually doing nothing but the optimization problem solving, and by converting it into a convex function, it is bit easier. You can do without log also, but it is preferable. That's all. So now, just what I'm trying to do, I'm just wrapping the sigmoid using log. Once it has been wrapped, I am just expanding the sigmoid function. Sigmoid of x is 1 by 1 plus e to the power minus x. And in our case, x is nothing but yi w transpose xi. So I am just unwrapping the sigmoid function. It is becoming 1 by 1 plus e to the power minus yi w transpose xi. That's straightforward. Then what I am trying to do, now this is log of 1 by x, right? So this is log of 1 by x, and log of 1 by x equals to minus of log x, right? So I am giving minus term here, and I am actually putting this term into upward. Okay, so this is now log of 1 plus e to the power minus yi w transpose xi. Now the last part, that is, we are actually finding argmax of minus fx. So we are actually finding max of minus fx, which is nothing but finding mean of fx. So what we are just replacing argmax with argmean, and the minus term is vanishes. So the maximum of a minus fx is similar to calculating minimum of fx. So this is our final optimization function for logistic regression. So we have to find the best weight vector, or W star, for which we can minimize this particular term. Okay. So in this video, we have learned many things. We have learned how the basic optimization function is actually not robust to outliers. It is affected by outliers and giving us the worst hyperplanes instead of the best hyperplanes. Then we tried out how we can overcome that using sigmoid squashing, and we have seen the properties of sigmoid function in details. And then a small explanation of what is convex function and what is non-convex function, and how we can make our optimization function for logistic regression as a convex function. So in the next video, I will show you like how we can fit the training, how we can best fit the logistic regression from this optimization point of view. So I hope you have enjoyed this video. If you like the video, please subscribe to my channel for future videos, and do share with your friends. And till then, have a nice day and happy machine learning. Thanks for watching.